NMOS region and this is CMOS region. NMOS and CMOS connector interior will form a CMOS. The mode of substrate junction is in reverse bias. So we will have an electric field in the division region of that junction pointing in this direction. Suppose somehow we have one or more stray electrons in the p-type substrate. They will be swept across the substrate or mode junction by the electric field and be attracted to the mode contact by the VDD. Let's focus on what happens as the electron flow out the VDD contact. As the electron moves through the resistive N-type mode material, it develops a voltage drop between the N-type material under the source and the VDD contact. Electrons flow in one direction means that the current will flow in the another direction. So this makes the region under the source slightly negative with respect to the source region itself. This will forward biases the source or mode junction slightly, which causes a hole or two to be injected into the mode from the P source. The holes will be attracted by the field across the mode substrate division region, and once they get there, they will be swept into the P substrate. Once the holes get into the P substrate, they will be attracted to the ground connection so that they can reach the semiconductor. As these holes flow past the N source and through the resistive P substrate, they build up a potential difference between the ground contacts. And the materials under the source with a polarity which tends to forward bias the source substrate junction and cause the electron to be ejected into the substrate. Electric field in this direction, the electrons in turn are attracted to the field across the substrate mode junction. Some of the electrons may recombine in the P region, but in today's high-quality substrates, there are very few active recombination centers, and so even though the electrons are minority carriers, they have quite a long minority carrier lifetime, and most of them make it to the substrate mode junction and are swept into the mode. Once inside the N mode, the electrons are then attracted to the plus VDD contact, where they build up a bigger forward bias across the source mode junction, causing more holes to be emitted from the source into the mode. These holes are swept across the mode substrate junction and flow to the ground contact. It does not take long before we have a dead short circuit between VDD and ground. This is not unhealthy for the integrated circuit chips in the list, and it's a process called latchup. Here's the symmetry of the latchup circuit. Now we consider the P source, N mode, and the P substrate as a PNP bipolar transistor, and the N source, P substrate, and N mode be a NPN bipolar transistor. The two transistors are intermediate, however, with the base of the PNP and the collectors of the NPN sharing the same N mode, and the collector of the PNP and the base of the NPN sharing the P substrate. The N mode and the P substrates are both collectors and bases at the same time. We need something to get this circuit started, so say we have a little collector current coming out of the top PNP transistor. This current will flow down through the resistor to the ground. As it flows through the resistor, it builds a little voltage which forward biases the base emitter junction of the lower PNP transistor and causes some collector current to flow into it. These currents coming from the VDD through the upper resistor and builds up a voltage across the resistor which will forward bias the base emitter junction of the top PNP transistor. This in turn causes some additional collector current to flow out of the PNP transistor.